Live streaming is on.
Good morning, everybody. Somebody has a microphone on, and there is a microphone feedback. Please. Hello? Please turn off your microphones. Hello. Today we have Philip Mannheim to give us a talk. But before I introduce him, hello? I still hear the microphone of somebody. Please turn off your microphone. This is a new seminar. There is no feedback. Thank you. Please remember that if you can't log into this seminar on Jitsi, you may watch it on YouTube channel with the title ILCACseminar YouTube. The seminar is also recorded on Indico, so you can look it up at later times if you can't be present. And please transfer this information to other people. There is also a website information on the Indico about this seminar, and you can contact Gianni Salme if you have any technical question. And today, Philip Mannheim is talking, but in 2 weeks, we'll have a talk by Peter Maris on wave functions, beta-salpeter amplitudes, and meson elastic and transition form factors. Philip Mannheim, who speaks today, is from University of Connecticut. He is a particle physicist who has a long career in basic issues of physics. He worked on unification models. He is interested in mass generation. And recently, he is participating in the explosive development astrophysics issues. And he also contributed to conformal gravity. And today, we will have his talk on comparing light from quantization with instant time quantization. And I will be happy to welcome Philip Mannheim and ask him to take over from me. Thank you. Philip, can you hear me?
Yes, can you put my slide up? Oh. Okay, is everybody able to see comparing light from quantization with instant time quantization? So then I'll begin. Well, first of all, let me thank the International Light Cone Advisory Committee for the opportunity to speak. I'm going to describe some work which contains some puzzles that I've had for a very long time, and some more recent work that originated in my very good fortune to be able to do a sabbatical at SLAC a couple of years ago with Stanley Brodsky and Peter Loudon, who are very active in Lightfront, and I started to learn about it. And it's managed to yield 4 papers that we published in various forms. One of them, which is very interesting, this is the LightCone 2019 that took place in Paris. It was the last time that we were able to get together physically, and we've had to continue virtually, and Stanislaw is doing a wonderful job in making this happen. So I want to describe this work, and I go next page. That's not what I'm supposed to go. I don't have to do. Okay. So the various issues, there are 3 questions that I want to address today. First of all, Lightfront quantization is at equal x plus, whereas regular quantization instant time is at equal x0. Are they the same theory, or are they different theories? Now, for many years, I puzzled over the question of, we had from gauge theories, we could quantize in equal A0, we can quantize in A3. There were different gauge choices. And the question was, are quantization conditions boundary conditions for solving differential equations? And if they are, then different boundary conditions means different theories. So the first thing that you would be inclined to think would be they might be different theories. What about the Hamiltonians? Are the Hamiltonians the same or different? That's the second question. One generates translations in x0 and the other generates translations in x plus, so they certainly look different. But if they are different, then which is the right one? Which is the one we're supposed to use in the real world? And then to answer that, we have to figure out, are the Hamiltonians even related? And I'll show you that indeed they are. Now, the third question was, is there anything in quantum field theory that is not accounted for by the on-shell Lightfront Hamiltonian description of physics? Does on-shell give you all of physics, or is there something else that we need to know about? And it turns out that there is something else. And the answer to all 3 questions are yes. So remember, first question is, are they the same theory or different theories? Yes, they are the same theory, even though the commutators and anti-commutators look to be so different, and we have to explain why they are so different if they turn out to be so different. Second question was, what about the Hamiltonian? Are the Hamiltonians related? The answer is yes, because of general coordinate invariance. x0 goes to x0 plus x3 is a space-time dependent translation. It is not a Lorentz transformation. And that is one of the keys to the talk I'll give today, because back at the beginning of Lightfront, there were big questions about the infinite momentum frame. And it's always thought that the infinite momentum frame has something to do with Lightfront quantization. And of course, going to the infinite momentum frame is a Lorentz transformation. But in fact, this is a space-time dependent translation. And the momentum generators associated with this, because any 2 translations are related by a unitary transformation. So in fact, the 2 Hamiltonians are unitarily equivalent. And later on, I'll show you how to construct the unitary transformation between them. Last point is there anything in quantum field theory not accounted for by on-shell Lightfront? The answer is yes, but only in the vacuum sector, and it's because of modes with p minus equals 0. My notation, p lower minus, is, I believe, what everybody else in the Lightfront community calls p upper plus, or twice p upper plus. I use the p lower minus because I use the coordinates to be contravariant, and I use the momenta to be covariant. Now, using the coordinates will turn out to be the key to what is going to be presented today. Mass shell conditions, P0 squared minus P3 squared, that those things are all standard. And you introduce P plus and P minus as the linear combinations, the analog of these combinations. And what you find is the instant P0 is well behaved at P3 equals 0, whereas the front P plus blows up at P minus equals 0. It's singular at P minus equals 0. That's called the zero mode problem, and we have to be able to deal with that. The key features of what I'm going to present: the light front Fock space is equivalent to the light front Hamiltonian, and both correspond to pole terms in Feynman diagrams. So as long as there are only pole terms, everything that is ordinarily done goes through without question. Instant time graphs written in the infinite momentum frame also correspond to light front Fock space and light front Hamiltonian description. However, and this was one of the results that Brodsky, Loudon, and I developed, in the vacuum, there are also circle at infinity contributions in Feynman diagrams, and with them, you might think that if that's only the case in light front and doesn't appear in instant, you would think that would make them totally unequal, but it turns out that what they actually do is they show that they are equal. So if instant time vacuum graphs and instant time light front graphs are indeed equal, instant time graphs don't have a P minus equals 0 mode problem because you're working with P3. Therefore, the zero mode problem must have a solution because it's equal to a graph that contains no P minus problem in the first place. So we'll see how we deal with that. Now let's go to the Fock space expansions. They're all very familiar. You just expand the field in terms of A's and A daggers. You expand the light front field, also in terms of A's and A daggers. Completely familiar, nothing at all unusual, except you do two things that are strange. One, you know that you asked, what's the commutator of A with A dagger? This is just an expansion for a free theory. This is just an expansion in terms of a complete basis of plane waves. A and A dagger are the quantum operators. What's their commutator? So we say it's a delta function. For the light front, what's the commutator of A with A dagger? We also say it's a delta function. But you're not free to do that. You can't just determine that the commutator of A and A dagger is anything you want it to be. It has to be fixed by something else, and I'll show you what that something else is in a moment. The other issue, of course, two separate issues. P3 goes from minus infinity to plus infinity, whereas P minus over here only goes from 0 to infinity. And on top of that, there's a singularity, there's a branch point when P minus is equal to 0. So the theory is singular at P minus equals 0. And if we now look at this factor here, x plus over P minus, it's not defined when x plus and P minus both go to 0. In the old language, that would be P plus, upper plus going to 0. So we see we have a problem if we let x plus go to 0 and P minus go to 0 simultaneously, and that will, resolving that issue will be the main point of this talk. Now, the light front Hamiltonian makes one further restriction. It restricts to P minus positive. And the reason that it restricts to P minus positive, we had a moment ago, and that was if P minus is 0, then P plus is infinite, and there are no, in a finite energy scattering process, you can't send in a beam with infinite energy. And therefore, the light front Hamiltonian never includes P minus equals 0. It's just excluded. Now, however, if we have a process which involves P minus equals 0, if we could find such a process, then it would be outside of the light front Hamiltonian approach. And where is the one? It's in the tadpole graph, vacuum 5-5 vacuum, which of course has x plus equals 0. These are at the same points, and the vacuum's translation invariant. And therefore, in this particular graph, which would just be 0 momentum comes in, and at the cross, and then you get momentum around the loop, because the momentum coming in at the cross is 0, the only momentum that is possible is 0 momentum. Therefore, the tadpole graph is pure P minus equals 0. Therefore, it's outside of the light front Hamiltonian approach with P minus positive. But also, all the points are 0, so it is both at x plus equals 0 and at P minus equals 0, which is exactly where the Fock space expansion fails. And therefore, from the beginning, we know that the Fock space treatment of this graph is not valid. If we could exclude P minus equals 0, then that graph would be 0. And if that graph is 0, this is a potential solution to the cosmological constant problem that Stanley Brodsky has pushed a lot, and I think it's a very nice idea. Unfortunately, it fails because of the indeterminacy of the limit of x plus going to 0 and P minus going to 0. So how do we, let's have a look at the instant time and light from commutators. How do we even determine them? Well, there's only one way to determine commutators. You start off with an action, you do the variation with respect to the metric, that gives you the energy momentum tensor, and then you construct the generators. These are the momentum generators required by general coordinate invariance. We impose the condition that the generators are the generators of translations, and therefore obey this commutation relation, and this is the equation. P, remember, the Lagrangian depends on the fields, therefore this is a nonlinear equation in the fields, and that fixes the normalization of the A's and A daggers. It fixes it to the one that everybody uses, but this is the basic requirement is that the momentum generators generate momentum translations. Now, let's have a look at the scalar instant time commutators. Here's the kinetic energy. You construct the conjugate. You impose that phi with phi d0, phi is a delta function, and you'll find that with this condition, you implement this transformation of the momentum generators, and that's the big paper that Stanley, Peter, and I have just published in Physics Reports, is how you do this in great detail. At the same time, you discover this same relationship requires that the commutator of phi with phi at different spatial points is 0. For the scalar light front commutators, you do exactly the same thing. You introduce differentials d plus and d minus in the obvious way, and then you find from this condition, the same condition we had a moment ago, from that condition, we find that this is the commutation relation. Now, in and of itself, it looks a little bit innocuous, except for the fact that this here, and this is the important point, this is d minus, it's not d plus. You get the canonical conjugate by taking the covariant derivative with respect to d plus phi, and the canonical conjugate is d minus phi. Now, d minus is not the analog of d0, so these two commutators are already different. But worse, because these are at equal x plus, but this is not a derivative in x plus, this equation can be integrated, and therefore you get this relationship here, and you see that the phi-phi commutator in the light front case is radically different from the phi-phi commutator in the instant time case. You can do exactly the same thing for gauge fields. For gauge fields, you will have a straightforward instant time formalism, but in the light front, you get the analog, you get d minus instead of d0, and again, you can integrate, and you can get that at equal times, but different spaces, the commutator of a mu with a nu is non-zero. So by using these rules, we find different commutators. Now, moreover, let's look at the momentum generators. The momentum generators are given by the T0 mu, but these are different. The light front will vary with respect to 0. The instant is 0 nu, and the light front is plus nu. So these are even different energy momentum tensor components. d3x becomes dx plus dx minus dx minus dx1 dx2. So those integrations are different. The surface terms are different because they're different components of the energy momentum tensor. So to show that the p mu's are even time independent or x plus independent requires different boundary conditions at infinity, and everything looks different. And it's no surprise then that the commutators come out different. As we'll see, it's not as bad as it looks. For fermions, life is even worse. For instant time anti-commutators, psi with psi dagger is the standard delta function. But when you calculate the light front fermion, the canonical conjugate, you just do the variation of the Dirac action, you find that it's a quantity psi plus, where psi plus is a projector operator acting on the field. So what happens is the commutator of 2 psi pluses is a projector operator, the lambda. Lambda plus is equal to a half 1 plus gamma 0, gamma 3. The two of them add to 1, they square to each other, they're orthogonal to each other. And most importantly, the gamma 0 is replaced by gamma plus gamma minus, which are gamma plus or minus gamma 3, and gamma plus squared is 0. So unlike gamma 0 squared, which is 1, gamma plus squared is 0, and that means that the gamma matrices are divisors of 0, which is why these are projectors, and projectors are not invertible. So we can't go from light front back to instant time, even if we wanted to, because of this lack of inversion. Psi minus you can construct from the Dirac equation. It's a constrained variable, but more than that, it's a non-local strain variable. It's an integral of psi plus. So this is called the bad fermion, and the psi plus is called the good fermion. So knowing that it's a constrained variable, we can still calculate the commutator of a psi plus with a psi minus, because we know the commutator of a psi plus with a psi plus dagger. And you evaluate it out, and you find it's this complicated object. And finally, you can calculate the commutator of 2 psi minuses, and this is even more complicated. It's a non-local derivative of a non-local integral in different variables. So it's quite clear that the commutation relations look very, very different. I must admit that when I got into the field, I found it very hard to even accept that these commutation relations and anti-commutation relations might even be correct in the first place. But that's why I decided to determine everything from the condition that the momentum generators are indeed generate translations. And there they are. Now, how on earth can we reconcile them? So instead of looking at the equal time, let's look at the unequal time commutators. And for the unequal time commutators, you can just calculate in the instant time the commutator of phi with phi 0. We're just working for massless fields. You can just work it through, and this is the standard answer that you get. The only thing I want you to notice is that in phi with phi, these are C numbers. These are operators, but the commutator is a C number. Now, the unequal time holds at all times. Therefore, it also holds at equal light front time. So we can evaluate this quantity. We can make the substitution. X0 is x plus x minus, x3 is x plus minus x minus, and so on. And we can reevaluate this quantity. And when you work it through, and then you set x plus equals minus x equals y plus, you find that phi at equal x plus is none other than the term that we just had a moment ago, namely this this expression over here for the equal x plus but unequal other components commutator. And so what we discover is that we can derive the equal light front time commutator starting with the unequal instant time commutator. And so the differences are not intrinsic, they're only because you took the unequal time objects and made the restriction to equal times. But now we see that all we have to do is work with the unequal time commutators and anti-commutators. We'll see how that works in a moment. And we come up with the very interesting result that light front quantization is a consequence of instant time quantization and does not need to be independently postulated. This expression here only uses the instant time commutator because you need to know what the A's and the A dagger commutators are, and you obtain the equal light front time as output. So the two theories are equivalent. They only didn't look equivalent because we went to equal times and equal light front times right away. As long as we stay away from that, then there's no problem. Exactly the same story for gauge fields. I'll just tell you the answer. Again, you can start off with the unequal instant time commutator and obtain the equal light front commutator. Similar results hold for non-abelian gauge theories as well. However, life's a little bit more difficult for fermions. For fermions, the unequal time anti-commutator, instant time, is just given by this relationship. But if you set x plus equals y plus, you can immediately get the good fermion commutator, anti-commutator. So that's what we want. So we've been able to go from unequal instant time to equal light front time for the fermions, but only for the good fermions. It turns out, and this is what we do in this big physics report, is you can also do the same thing for the bad fermions. So what we discover is that in all these cases, light front quantization is instant time quantization, does not need to be independently postulated. The seemingly different structure between equal instant time and equal light front time is a consequence of the similar structure of the unequal time sectors. And so the only question is, under what conditions will these equalities hold? Answer the general rule. Any two directions of quantization that can be connected by a general coordinate transformation, and x plus is equal to x0 plus x3 is one of them, precisely because the unequal time commutators are general coordinate invariant if you start off with a general coordinate invariant action. And therefore, you can make general coordinate transformations. They're just C numbers. You're just changing the coordinates. We'll have to ask in a moment what happens to the fields under this transformation. We'll come back to that in a moment. But the general rule is, as long as two directions can be connected by a general coordinate transformation, they describe the same theory, and they're not, in fact, different boundary conditions. They would, of course, be different boundary conditions if you didn't have them general coordinate invariant equivalent, but then you would be working in a theory that wouldn't be general coordinate invariant in the first place, and those theories seem to have nothing to do with nature.
Philip, sorry to get silly glossy. I have a question. So, what can you say in the case of interacting fields?
We'll get to interacting fields in a moment.
Okay, thank you.
The answer to your question is, while the free theory commutator is a C number, the interacting theory commutator is certainly not. And for the interacting theory, I can only do matrix elements, and I will use the Layman representation. And we'll do that. If I get that far, we'll do that as well. Massive fields, let's look at the scalar case. Now, for massive fields, the equal time commutator for time-like separated depends on the mass of the field. For light-like, it doesn't. And for space-like, it's 0. Now, if you take this function here and you let m go to 0, it doesn't vanish. It does not vanish when m goes to 0 because J1 goes like m, and you've got another m, it goes like m squared. So, I'm sorry, I said it wrong. If you let x minus y squared go to 0, J1, that one over that one is well behaved. Therefore, going from time-like to light-like, you get a discontinuity. Similarly, going from light-like to space-like, you get another discontinuity. Therefore, this is a discontinuous function of the separation, x minus y squared. It shouldn't surprise you. You can't go continuously from time-like to light-like. And you can't go continuously from light-like to space-like. But that means that this function that I've written up here at the top is discontinuous. Now, we could have guessed it must be because it has these epsilon factors, and epsilons are not functions, they're distributions. And so how do we describe them? Well, epsilon of t, theta of t minus theta of minus t, and delta of t are distributions, and we can write theta of t as a contour integral. And when t is not equal to 0, we can suppress the circle at infinity, and this just becomes an integral with the pole contribution and gets the theta of t. But what happens when t is 0? In t is 0, which is the vacuum case, there's no suppression factor, and therefore the circle at infinity contribution can't be ignored. And if you calculate theta at t equals 0, you get a pole term and a circle term, and the answer you finish up with is a half. Namely, you get the 1 from the pole minus a half from the circle, and the answer is a half. Therefore, we see immediately, we know we're going to have to go into the complex plane, and when we go into the complex plane, we have to worry about suppression factors. So I can rewrite this expression as a contour integral in the P. I can introduce a variable P0. I go off shell. P0 is no longer equal to EP, and I get this expression. And now to deal with it, I want to get the denominator into an exponential, so I use this exponential condition. And the I epsilon has the sign that it does, so that the alpha equals infinity contribution to this integral is 0. So when you do that, you can then do all the momentum integrations, and you finish up with this particular expression. And we'll come back to that in a moment. And you see the epsilon term appears because the theta functions are telling you which way to close the contours. Plus I epsilon means close below, and minus I epsilon means close above. And then when you take this expression and you evaluate it, then you get all these results over here. And that's exactly what you would like. Now let's do the light front. Well, we make the same light front expansion as before. And now we go ahead, and again, we have a P minus problem, but now we can solve the P minus problem by first of all going back and doing a P plus, going off shell and doing a P plus contour integral. And now I get 4P plus P minus that is on the denominator. And of course, at the pole, I would get the 1 over P minus. But I don't have to do it that way. I can use the exponential regulator, the one I introduced you here a moment ago. I can use that exact same one. And then I can put the P minus into the exponent. And then I can do the P minus integration. And when I do all the integrations, I finish up with this expression, 8.2. And you just go back and you see, bingo, this is exactly the time translation invariant. X0 minus Y0 goes to X plus minus Y plus. And so you can see immediately that the two light front unequal time or unequal everything are the same. And therefore the two theories are identical. You can now do this evaluation, and the important point to notice, and this is the important point, is here I have X plus plus minus Y plus. Remember, I made a contour in the P plus plane, not in the P minus plane. However, if I look at this function X minus Y squared, I can write it out here. X minus Y squared is equal to X plus minus Y plus X minus minus Y minus equal, and so on. That function, if it's positive or 0, X plus minus Y plus and X minus Y minus have the same sign. And therefore, I can replace X plus minus Y plus by X minus minus Y minus. And therefore, the expressions that I really want to compare, and now initially they don't look the same because this is X0 and that's X minus, but that's because this is multiplied by a function, which is a function of X minus Y squared. And so we established the issue, which is we wanted to get the X minus minus Y minus, because remember from the very beginning, we had this peculiarity that the light front, where's it gone? Sorry, the light front has this, take one back. The light front has this epsilon of X minus minus Y minus, and we've seen that it even naturally occurs. For fermions, I'll just state the results. I don't have the time to go through it, but the important point is for fermions, you must start in the light front with the 4-component fermion, not with the 2-component, not just with the good fermion. These are 4-component fermions, therefore in the fermion sector, you need the 4-component ones. You have to include the good and the bad fermions. And now afterwards, then you apply the projectors. And I'll just show you what you do when you do all that calculation. And these are exactly the same ones that I showed you earlier. And so the rule is, and this is the important point, the rule is that if you want to work away from equal instant time, equal light front time, you must use all 4 fermions. The bad fermions may be bad because they're constrained on shell, but these aren't, we're working off shell. And so the off shell, the bad fermions are just as important as the good fermions, and there's no distinction between them. Only when you go on shell and force the solutions to obey the Dirac equation do you have that problem. But we've seen all along, we're constantly going off shell. And so off shell has more information than on shell, and that's why these theories work. Now for unitary equivalence. So far we've discussed C numbers. Now let's look at the operators. We have these two relations for the Poincare invariance. We're assuming the Poincare invariance holds to all orders. Somebody asked me a moment ago, what about interactions? We're going to assume that the interactions are such that a Poincare invariance continues to hold. We can construct the unitary transformation which implements these transformations of the P0 and the P3. P0 is x0, so that goes x0 plus x3, and P3 is x3, and that goes x0 plus minus x3. So now we apply U to the field, to the instant time field. What it does, it changes the coordinates of it changes the argument to x0 plus x3 and x0 minus x3, and we see that that's the light front. So what we discover is that the instant time fields under this unitary transformation, and it's just a translation, gives you the light front field. Similarly, you can show that the vacua are related by the same unitary transformation, because this is always true in quantum mechanics of translation invariant theories. That's always the case. It doesn't matter that x3 doesn't commute with p3, as long as it commutes with p0, which it does, that's all that counts. Now, when you apply this, you just put in U dagger U in the usual way, and what you see is that matrix elements, instant time commutators, are equal to matrix elements of light front commutators. We thus establish the unitary equivalence of matrix elements of instant time and light front commutators to all orders. Next. For the layman representation, I'm a bit running out of time, so I'll just state the result, that the transformation must send P0 to P plus, must send P3 to P minus. The eigenstates doesn't affect the coordinates, but it acts on the states. And you do the same analysis, and you find exactly that the two matrix elements are equivalent. Now let's go to the Hamiltonian. The momentum generators can be written if they have a real and complete eigenspectrum, which we take to be the given for any field theory. The momentum generators can be always written as ket, energy eigenvalue bra. In the light front, it's exactly the same thing. These are now the light front momenta, and those with the instant time momenta. Now we apply the unitary transformation. The unitary transformation on P0, let's see what it does. It acts on the state, acts on the other state, but it doesn't touch the energy eigenvalues because numbers don't change under a unitary transformation. Eigenvalues don't change. So this becomes, IT becomes light front, IT becomes light front, and P0 we can rewrite as P plus plus P minus. That's just its definition. And therefore, we see that P0 IT is equal to P plus plus P minus light front. So the light front P plus is not equal to the instant time P0. On the contrary, P0 generates translations in time, but P plus plus P minus does as well. P plus generates translations in x plus plus x minus, in x0 plus x3. P minus translates x0 minus x3. The two together will only generate x0. So the momentum, this is a Hamiltonian, this is generating time x plus translations in light front case, is quite different than P0. They're not the same. However, it turns out that we can still get away with something. There initially appears to be a mismatch between the eigenstates of the two operators. Now, for any time-like set of instant time momentum eigenvalues, we can Lorentz boost P1, P2, and P3 to 0. And therefore, in instant time, we can get P0 equals m. So now the question is, what do we mean by non-relativistic in the light front case? Do we mean P minus equals 0? The answer is no. We still mean P1 equals P2 equals P3 equals 0, because that sets P plus equals P minus, and that sets p squared is equal to m squared, and therefore we go to p1, p2 equals 0, but p3 equals 0 means p plus equals p minus, and therefore p0 is equal to m, and p0 is equal to m. So the two Hamiltonians are not unitarily equivalent because we have the p plus plus the p minus, but when working on any state in the instant time rest frame, they give exactly the same eigenvalue. And that's what we really need. In the instant time rest frame, the eigenvalues of p0 and so I go now to p upper 0 and p upper minus, which is the same as p lower plus, that's maybe you're more familiar with that, they coincide. So in that sense, the two Hamiltonians are equivalent. They're equivalent when acting on a complete set of eigenstates, and that's all you ever need. You don't need them to be operator identities. They only have to act on these eigenstates, and so you do everything. If you work in light front, you must work in the instant time rest frame, not in the light front rest frame. Namely, you must work in p plus equals p minus, not in p plus, not in p minus equals 0. Okay, so, and somebody asked me, and we can see that this is completely general because we're just assuming Poincare invariance to all orders and unitary equivalence of translations, and therefore this holds to all orders. So now that we've established the equivalence of commutators and Hamiltonians, we now have to go and study Green's functions, namely time-ordered products, to see what happens there. Now, I'll be very brief. Let's see where life changes. If we take the tadpole graph that we have here, I'm going to construct it. I'm going to start with the unequal time propagator, namely the time-ordered propagator, not the two-point function. All discussion of these tadpoles in the literature starts with phi of x, phi of y at different x and y, namely you take the two-point function. I'm saying no, you start with the propagator, and you'll see why. Because the propagator is going to contain both time orderings, and we'll need both time orderings. Anyway, you can write it out in the free theory. It's just a Feynman integral, and then you let x mu go to 0, and you put x equals 0, and you just get 1 over p squared minus m squared. So now let's look at what's going on. Let's just look at this function very carefully, and you'll see that the whole answer. If you work in instant time, as long as x0 is non-zero, this will suppress the circle in the upper half plane, or the lower half plane, I'm sorry, and only the pole term will contribute. For the front theory, if x plus is non-zero, same story, you suppress the circle and only the pole term contributes, and you can count, when you calculate the pole term here and you calculate the pole term there, I'll show you that in a moment, you'll find you get the same answer. And so, as long as we stay away from x mu equals 0, instant and front not only coincide with each other, but they also coincide with what you get from the right front Hamiltonian. Now let x mu go to 0. For the instant, I've still got a 1 over p0 squared. I still have it. And that's still enough to suppress the circle at infinity, because it's dp0 over p0 squared. However, for the light front, I only have p plus p minus, and so I have dp plus over 4p plus, and I'm no longer able to suppress the circle at infinity. So for the first three cases, including the instant vacuum graph, only poles contribute, but for the tadpole in the light front case, you have to include the circle. So the complex p plus plane discussion is completely changed because it's not suppressed. So let me just show you. I just calculate the instant, just do this integral, instant time, I get this answer, it's just a Bessel function. I do the Fock space expansion, I get exactly the same answer, and show for instant time, the instant time Feynman and Fock space prescriptions agree, as long as I stay away from x0 equals 0. In light front case, a little bit more complicated. The poles are located as described. We only have P minus positive, so if P minus is positive, all the poles right below the P plus axis. We do the evaluation, we get this expression, and let me just show you what happens here. I've got to worry about the P minus equals 0, so I put in a delta function, a delta term to protect me from the singularity for the moment. I set alpha is x plus over 4p minus, and I get this expression, and that's the pole contribution to this integral. And then I notice the following, that if x plus is not 0, I can let delta go to infinity, and if delta goes to infinity, lo and behold, I get exactly the same answer. The pole contribution to the instant time graph is exactly the same one as for the light front is exactly the same one as I got for the instant time. So there, everything works, and you can see immediately what's going on, but what happens if x plus is 0? Something else is going to happen. So there's no ambiguity as long as x plus is non-zero, and we get the front pole contribution is equal to this expression, and you can do the Fock expansion, you get exactly the same. So the general rule is the Feynman and Fock prescriptions will coincide when the only contribution to Feynman contours is poles. Thus for x plus positive, the Feynman or Micron Hamiltonian approaches coincide, and everything that you do in one and you do in the other, you'll get the same answer, except, as Stanley Brodsky has been telling us for many years, the light front Hamiltonian is simpler. It's much easier to work with, but you don't have to worry. You're not going to getting anything that you weren't getting in the x plus case, but in the instance case, except what do we do about the 0? What do we do about the 0? If we just set x to 0 in that expression, the one that I showed you, just set the e to the ip dot x equals 0, all I have are the pole terms, and so I get this answer for the instant. That's the one that's the standard answer. Now for the light front, if I do exactly the same thing, if I first of all set the exponent to 0, and I do exactly the same thing, I work it through, don't worry about the algebra, I get exactly the same answer that I would get if I did the Fock space if I set x equal to 0 in the Fock space where I had the e to the I f x plus over delta. So if I just tell you, if I do the light front vacuum case exactly as before and I just keep the pole and the Fock space contributions, they are equal to each other, which they should be, except the answer dp minus over 4p minus doesn't depend on m. If you just take, and this is the clue, if you just set x equals 0 and you do the calculation, you do the pole term, you do the Fock term, and the answer doesn't depend on m. But you started out with an expression that did depend on m. So where did it go? Where did the m go? The answer is we left out the circle at infinity. And the reason we have to do that is because in this contour integral, the circle is not suppressed because it's p plus over p plus. And so we see now something really remarkable. Not only is the circle not suppressed, but we've even lost the m dependence if we just stick at the pole. Because we have a pole which is p1 squared plus p2 squared minus m squared, but the contribution, the residue is 1. The residue is independent of the mass. And therefore, unlike in the instant time case, where you have a double pole, p0 squared minus ep squared, p0 minus ep, p0 plus ep, the residue does depend on the mass. Here, the residue of the pole does not depend on the mass, and yet we started out with a mass-dependent function, therefore something went wrong. However, what is interesting is we didn't get 0. In fact, this integral diverges. We get an infinity. We don't get 0, which is the expectation if we restrict it to p minus positive, because the p minus equals 0 contributes. And so let's see that in more detail. So how do I now do the calculation? Well, I have to introduce, because I've got the 1 over p minus, I introduce the regulator. And now I can do the complete calculation, and you just follow it through. You do it in the usual way, and you get the difference of the two exponentials, which is the sine. And now, when you let the radius of the circle grow to infinity, namely on the circle, that becomes a delta function, and this graph becomes delta for alpha p minus. Alpha is positive, so that's delta p minus, And that means that the entire contribution is from the p minus equals 0 nodes. So when you do the calculation carefully using the regulator, you get exactly this answer. You get -1/32. That was from the upper circle. You get the same answer from the lower circle. You add them together, you get -1/16. And that's exactly what we had in the instant time case. So even though the circle terms are different in the two cases, it's because of the circle that you eventually, first you restore the dependence on mass because it never goes away. It's up in the I epsilon, it stays there because it's not a residue anymore. This is just a regular integral once you've done the regulator. And you get the answer that you would have got in the instant time case. And one of the novelties of this calculation is not so much introducing a regulator, but using a regulator on the circle. And we need to get the suppression, and we will get the suppression as long as we're on the upper half circle. We need this one. On the lower half circle, we'd have to have a minus I epsilon, but that's okay. And then you can do that calculation. Okay, so again, light front quantization is instant quantization. And even though there is only a circle at infinity contribution in the light front case, it is this circle at infinity that enables the light front and instant time vacuum graphs to be the same. Okay. So I won't go through all of this, but I just want to say something very quickly about infinite momentum frame. In the infinite momentum frame, you can send A0, makes this is a Lorentz boost in the 3 direction. A3 behaves like that, and you will discover that A0 squared minus A3 squared is boost invariant. It's equal to A plus A minus, and it remains A plus A minus. And if you remember Jerry Miller's talk a couple of weeks ago, he pointed out that these combinations are boost invariant for a boost in the 3 direction, and that was something that he and Stan Brodsky have been working on, which is a very convenient way. I think they did X plus P minus, but it doesn't matter. Nonetheless, this combination is boost invariant in the 3 direction. Of course, it's not boost invariant in any other direction, but that doesn't matter. Now we write 1 minus u is epsilon squared over 2. We're going to go to the infinite momentum frame. And the important thing that we discover is that dp3 over ep goes to dp minus over p minus, which of course you'd expect because that is the argument. The dp3 over ep in the instant time becomes the dp minus over p minus in the front time. So that's what you expect. Now let's write down the instant time vacuum graph. It's only the pole term. It's d3p over 2ep. We go to the infinite momentum frame, and it becomes dp minus over p minus, just as it's supposed to be. And that exactly, as I showed a moment ago, that is, if I have it, that is the Fock space contribution, and it's the pole term contribution. And so the infinite momentum frame is doing what it's supposed to do. What it does is it converts an instant time pole into a front form pole. And that's what it's supposed to do. Except there's something very strange here. The thing that's very strange is that d3p over ep has come to become this form. The pole terms have transformed into each other. The Fock spaces transform into each other. But we know that this is the wrong answer because the mass dependence has gone. This is the real answer, the one we just did from the circle at infinity. So something goes wrong. Even though this is a completely standard prescription, something goes wrong. And there are two puzzles. First of all, how could we lose the M dependence to begin with if we're making a Lorentz transformation? And secondly, how do we get the M dependence back? So we have two separate questions to answer. Now the answer is the quantity dp3 over 2ep is Lorentz invariant, we've done that all the time, provided you transform with the velocity less than the velocity of light. On the other hand, in the infinite momentum frame, you're transferring with the velocity of light, and it becomes a quantity that's independent of mass, which is not surprising. In the infinite, if you're going at infinite velocity or velocity of light, infinite momentum, then you don't know anything about mass. But this is supposed to be Lorentz invariant, and I've made a Lorentz transformation. The answer is velocity less than the velocity of light and velocity equal to the velocity of light are inequivalent. because an observer that is able to travel at less than the velocity of light is not able to travel at the velocity of light. So invariance under velocity less than the velocity of light preserves the mass dependence. At the velocity of light, it removes it. And that is very serious. But that means we've lost it, so how do we get it back? Well, now we go back to the light front, to the instant time expression. We have the pole terms, and we do them as we usually do. But now let's look at this graph in the infinite momentum frame. Now P becomes suppressed in...
Live streaming is on.
It suddenly becomes not suppressed when you go to the infinite momentum frame, and that's where the infinite momentum frame fails. Now, as regards interactions, I've shown you with the layman and so on, but let's just consider very, very quickly. Path integrals and Feynman diagrams are the two ways of dealing with interacting theories. They both involve C numbers. One, path integrals involve integrals of classical variables in coordinate space. Feynman diagrams involve integrals of classical variables in momentum space. So these are numbers, these are not operators, these are matrix elements. In both cases, we can transform from instant time to light front time, and either coordinates or variable or momenta, using general coordinate invariance. Therefore, if the theory and its renormalization procedure are general coordinate invariant, the equivalence of the light front of the instant time and light front Green's functions is established. Now, there is a caveat. For Feynman diagrams, we need to start out with a fully covariant four-dimensional contour integrals if we want to establish the equivalence. Now, we can obscure the equivalence if we do the pole integrations in the complex frequency plane, as then we finish up with three-dimensional integrals, and in those three-dimensional integrals we have a zero momentum problem. So the zero momentum problem is not it's not intrinsic, it's because you did the contour integral in the wrong sequence. You do the regulator version, and then you can take the limit P minus goes to zero. So the zero mode problem is avoidable because you just did the contour integral in the wrong way. Well, if you start off with the three-dimensional integral, then you're already on shell, so you effectively have done the contour integral, even if you never said so. So that's where the problem comes in. It's only when you go on shell too early. Now, why must it be avoidable? Why must the zero mode problem be avoidable? Because in the path integral approach, you're only in coordinate space. There are no momenta. There's no momentum integration. It's all coordinates. Therefore, it can't possibly have a zero momentum problem. But the path integral is equivalent to the Feynman diagram. Therefore, the Feynman diagram can't have a zero momentum problem. Why did you get one? Because you did them on shell and you weren't doing Feynman contours. So finally, the moral of the story is the following. When we let P minus go to zero, we're letting P plus go to infinity. But X plus is the conjugate of P plus. And thus, as P plus goes to infinity, X plus goes to zero. Therefore, the P minus going to zero and the X plus going to zero limits are intertwined, and you have to handle that limit very, very carefully. And as we've seen, it leads to the introduction of circles at infinity. If we stay away from X plus equals zero and we restrict to X plus positive, then P minus is also positive, and that's the light front Hamiltonian approach. There is no difficulty, as there are only poles and nothing is singular. With forward scattering, which means X plus positive, forward scattering on shell light front Hamiltonian approach is completely validated. But for tadpoles, let's see what happens when X plus go to zero. We have the T product, we have theta of X plus and theta minus X plus, they both go to zero. And therefore what we get is we get a forward propagation and a backward propagation. That's why I use the T product, not the 2-point function. Because in the limit of the T product, I also have the backward contribution, and that's absent in the standard on-shell light front Hamiltonian, and that's why we found that the instant time, the light front vacuum graph is not only non-zero, it's even equal to the instant time one. Now, finally, I would notice we can transform each instant time graph into each light current graph by a change of variable. However, that does not mean that pole equals pole or that circle equals circle. It only means that pole plus circle equals pole plus circle. And it's only on the fully closed contour that the integrals are equal. Once you go to the pole, they don't have to be equal. And that's the distinction. So finally, the transformation x0 goes to x0 plus x3, x3 goes to x0 minus x3, is a space-time dependent general coordinate transformation. It's not a Lorentz transformation. And thus, by general coordinate invariance of the fundamental interactions, it must be the case that light from quantization is instant time quantization, just one theory. Thank you very much.
Thank you, Philip. Before we started, hello?
Yes, I'm right here.
Please turn off your mic when you're not actively participating. Paul mentioned to me that Volodya Karmanov wanted to say something. We are over time limit for the talk. So Volodya, in order to, I hope Volodya is with us. Are you there?
Yes.
Okay. So Philip mentioned that Volodya wanted to say something. We have half an hour for discussion in principle. So,
okay.
Volodya, please, but we did not yet have any question from the audience concerning Philip's talk. So, Volodya, if you can say something quickly so that participants can discuss Philip's talk in conjunction with your statements, then we can perhaps have a discussion. But please don't extend it too much, okay? I'm sorry for asking, but we went far over time with the talk. Volodya, please take the floor.
Okay. Do you hear me?
Yes, I can hear you.
Okay, good. So I would like to say that I completely agree with Philip concerning equivalence of light front form and instant form, but I have impression that it is in this part, this is known. For example, first take free fields and solve Klein-Gordon equation and impose commutation relations between creation and annihilation operators and calculate commutator for arbitrary times, and then go to on the light front and on the instant plane t equals to 0, and we reproduce the global commutator. So two approaches are equivalent in the free theory. But if we take interaction, we can start with T product, exponent is T product, and then replace this T product explicitly by theta functions, either in T direction or in the light con time. And in both cases, the first case was considered long ago by Kadashevsky in 1964. The second case was considered in my paper, and later it was published in our physics reports in 1998. And in both cases, we reproduce either amplitude corresponding to instant form or light front form. So since they are obtained from one source, they are also equivalent, and therefore I agree with this statement, but I have impression that it has been already known, maybe not realized by scientific community, but this result is natural and it has been known. Thanks.
Thank you. Thank you, Volodya. I understand that the talk by Philip is now open for discussion. Of course, please start, whoever has a question.
Okay, this is Changji. I would like to say some comments about what Philip talked about and also what Karumarov mentioned. I feel like I'm obliged to talk about some comments because some of you may know that I have sort of connected the quantum electrodynamics from instant form dynamics to the light front dynamics using the method people use, the so-called interpolation angle method, connect between the two. So I think all the things that Philip and Volodya mentioned, I think I agree with all the things said. But I just mentioned something that was not said in Philip's and Volodya's mentioning. That was this actually the difference in the helicity in the instant form dynamics and the light front dynamics, which was discussed in that interpolation method. There, I could see that the instant form dynamics, there is a usual Jacobian weak helicity, but in the light front helicity, that is actually different in the sense that Jacobian weak helicity depends on the reference frame. If you go faster than the particle when the particle has a mass, the helicity flips. However, in light front dynamics, it doesn't. It's invariant under the reference frame, and that can be shown by making this interpolation angle. And then we find actually there is some critical interpolation angle which actually divides this branch of Jacobian weak helicity, but the light front helicity. So that was discussed. And also, by going through this, I think that really the two theories are same, but there are some effectiveness of the calculation. I think Philip mentioned some of that, but I think that's my understanding is that that's the change of the degrees of freedom. In other words, the one particle in light front dynamics doesn't mean it's a one particle in instant form dynamics, and it could corresponds to many particles. And all these zero modes that Philip mentioned could correspond to many, many particles as kind of collective mode can be thought. I think that's essentially what I wanted to say. And also this lengthy discussion about this integration that Philip mentioned about this arc contribution. I think one of the key things is that the pole in the light front dynamics is actually a moving pole. It's different from instant form dynamics. It's like an I epsilon divided by P plus. So whether you take a P plus positive or negative, it's moving. And when P plus goes to 0, this moving pole goes to infinity. So one has to catch that moving pole. Otherwise, you don't get the same result as the covariant Feynman diagram calculation using dimensional regularization. Of course, one has to all agree with what the result is. So that's all the comments I wanted to say, but I don't really have any real disagreement.
Thank you. Any other? Hold on. There are too many people at the same time.
Can I respond before we go to any more comments?
Sure, you can. Philip has the floor.
Okay. First of all, I very much.
Hold on, Philip. Hold on.
Yes.
Anybody who is not speaking, please watch your microphone and don't turn it on simultaneously with Philip's. Now Philip's is speaking.
Yes, a couple of comments. First of all, Valoidia, thank you very much for your discussion. I'm delighted to know that you agree that light front quantization is not different from instant time quantization, and I'm happy to learn that this had been considered very early in the development of the field, and it's a good result. And thank you for letting us know about that. Now, for Mr. G's remarks, I don't know if you can still see my screen. My equation 13.1 shows exactly that the poles in the light front case are moving poles. And that's exactly as Professor G described. And you have to allow for that in calculating the propagators. Now, the other thing that I wanted to say, which I think is not something that I'd stress, but I can see immediately where it comes in. I don't know if you can still see my my slides. You can see that P0 IT is equal to P plus P minus light front, and so what happens is that one state in P0 of IT is one state in P plus P minus, but is many states in P plus and P minus separately, because you can add P0 plus P3 to make P plus in many different ways. And so he's absolutely right. One body in P0 is indeed many body in P plus. And the other remark he did make, yes, the poles are at I epsilon over P plus. And yes, I agree with that. And that's something I'd mentioned. The issue of the Jacob Wick I haven't looked at. One of the things that we did in the physics report was we did not quantize gauge fields in the light front gauge. We did not set A plus equals 0. Well, we did that as well, but we also use gauge fixing. And gauge fixing is covariant. And so I don't know, I do know that if you do gauge fixing, you don't get any zero mode problems. And so that was why I thought it was interesting. But I don't know what happens to helicity eigenstates in that case. But I think that there may be some concerns that Professor G mentioned that may just be due to a choice of gauge. Those are my comments.
Yeah, one thing I just mentioned that we did this gauge changes from instant form dynamics to the light front dynamics, and what I found was that the so-called Coulomb gauge in instant form dynamics is connected to the gauge in the light front dynamics, light front gauge A plus equals 0, and then you can sort of see how continuously they are going back and forth. And helicity, the difference is of course somewhat related, but it's not really just the gauge degree of freedom issues. It's actually more about this longitudinal boost is kinematical in the light front dynamics, but it's not in instant form dynamics.
Any other question or comment?
Yes, Stan, this is Daya.
Okay, speak please.
So my questions are rather naive to Phillips. Why is it reflecting? It's coming back all the time. Oh, usko band karna. Just 1 minute. Yes. I'm sorry. There was some interference from Usha. No. Oh. Hello. Are you able to hear me? Phillips, are you able to hear me?
Yeah. Yes, I'm able to hear you, but I have to mute.
What do I do?
No. Hello?
Hello.
Go ahead, please ask your question, and please watch your time so that we have other people also allowed to talk. Thank you. Hello? Daya? Daya?
Yeah.
Hello?
Hello. Yeah.
Daya, if you want, you can... Go ahead,
What do I
speak.
do? The Poincare invariance that you mentioned is a space-time symmetry, and the questions about writing commutation or anti-commutation relations, they have to do with the internal symmetry of the theory. If the theory has gauge invariance or not, accordingly, one has to think if it is gauge invariant, then one has to worry about gauge fixing. And then one cannot talk about the commutation or anti-commutation relations without mentioning the gauge fixing. Or do you assume that everything that you are addressing to is related to the theories that do not have gauge invariance? Because Poincare invariance is a space-time symmetry and not an internal symmetry. Could you make some comments on this?
Yes. The two things are important for constructing the momentum generators. First of all, you have to construct the energy momentum tensor using the covariant description, namely the variation with respect to the metric. You can't use the canonical energy momentum tensor. You will run into gauge problems. You run into problems that they're not even symmetric, but none of these problems exist if you have a gauge invariant action and a general coordinate invariant action, and you construct the energy momentum tensor by varying with respect to the metric. Now, the second question that you raise is, what is the you're really asking the status of the layman representation in a gauge theory. And the answer is that it exists, and it's well established. In fact, it was first established for QED. And it's quite straightforward. And the momentum generators discussed the way I've described them, namely by starting with the energy momentum tensor, are automatically gauge invariant, and they automatically have a complete spectrum. And the only thing that you need for the layman representation is that the spectrum be complete. Now, that doesn't mean that you can easily calculate the spectral function. You can't easily calculate it, but that it exists is the only thing that matters. And the only point that I was making today was that the spectral functions of instant time transform into the spectral functions of light front because they're defined by the eigenstates of the momentum operators. And that, I think, is perfectly okay. You are correct in saying that when I write down the momentum operators, they're going to contain the gauge fields. That's fine. I mean, that's not in dispute. So if you had a concern about gauge invariance, then that concern would have been met in deriving the layman representation in QED right at the beginning when it was first introduced. And all I'm arguing is that the same analysis that's done in QED in instant time goes through in QED in light front time. But there is an issue which Professor G touched on, and that is you have to be very careful about how you implement a choice of gauge. And that's why I do the gauge fixing, because it's covariant. So gauge fixing is a covariant procedure, and that one doesn't give me any difficulty. Professor G mentioned that the Coulomb gauge and the A + = 0 gauge are equivalent, and that's actually something that we've also, that Stanley, Peter, and I recognized in our big physics report, and we get around that by using gauge fixing instead.
Okay.
Any other questions?
Thank you.
Hello? Any questions or comments?
I have a question, Jerry.
Go ahead.
Yeah, I think I understood your talk. I want to go back to the beginning. I have a question. I'm talking. You started writing the expansion in the light front, pointing out the problem with the 1 over the square root of P minus in the expansion. Is the expansion of the field in terms of creation and destruction operators correct or not? I mean, does that give you everything? I'm still confused about that. Is that first expansion with the 1 over square root of P plus okay?
If I can respond to that, the answer is absolutely yes. However, the subtlety is the following. In that expansion of the field, you're expanding in terms of a complete set of solutions to the wave equation. And that basis is the right basis. Now, what I showed you is that dp minus over 4p minus to the half has to be there by Lorentz invariance. That's what I discussed a little bit later on. There's no choice. That puzzled me at the beginning. How could it be there? And the answer is it's required by Lorentz invariant. And that gives me coefficients in the expansion, which I call A and A dagger. But I don't know anything yet about whether or not the commutator of A with A dagger is a delta function. I don't know that. I can't just say that it is because it is in instant time. That's why I used the momentum generator, P mu phi is I minus I d mu phi, to fix the canonical commutators. And then when you fix the canonical commutators, you find that the A and the A dagger do obey A dagger is a delta function, which then means you can interpret them as creation and annihilation operators. But that's not true a priori. Just by writing it, all you've done is you've said, when you introduce the A and A dagger, is all you've done is said that the solutions to the Klein-Gordon equation are complete. You haven't said anything beyond that until you put in the dynamics. And the dynamics, in my opinion, comes from the requirement that the momentum generators generate translations. Now, once you've done that, you discover that the commutator P mu with phi is minus I d mu phi is well defined. It doesn't blow up at P minus equals 0. It holds for all momenta. And that's the important point. And then I can take matrix elements and I can propagate fields with these operators, with the P, e to the I P mu, x mu, and so on. And that means that the Green's functions are going to be invariant. And therefore, the P minus the P minus 0 is a bogus problem. And the way that I've got round that is by not working in a three-dimensional formalism to begin with, but by working off shell. I think if you do work on shell, you can run into apparent problems. They're not real and you can resolve them, but it turns out that it's much better to work off shell.
Barry, are you happy? Hello?
If you just calculate scatter, I'm happy. But if you just calculate, I'm trying to see where this matters. If I just do an ordinary calculation, do I have to worry about zero mode? I've never seen a need to worry about them, actually.
The answer is yes, you do not need to worry unless you look at vacuum graphs. Now, vacuum graphs aren't even measurable in ordinary quantum field theory because you're working in flat space. It's only in curved space that when you couple to gravity that you even need to consider them, because you can always normal order them away in the standard theory, because basically in any calculation that you do in flat space where you ignore gravity, you're only calculating energy differences. You're not calculating energy. But gravity couples to energy, and therefore the tadpole graph is important in gravity. That's why there's a cosmological constant problem in gravity and nowhere else. And then you do have to be very careful with the zero mode.
I see. Thank you. I understand. Thanks. That's helpful.
Any other question?
Gianni Salmè from Rome. May I add just a small piece of information to what Volodia said? Already in the 70s, Sokolov and Shantny demonstrated the equivalence between the front forms and the instant forms of relativistic Hamiltonian theory. I mean, they demonstrated that the same S matrix can be obtained by explicitly constructing the unitary transformation that relate the two forms of the relativistic Hamiltonian dynamics. Thanks.
Thank you. We still have about 5 minutes to go. If somebody wishes to speak, please go on.
I could say something. It's Stan Brodsky. So,
Stan Brodsky, go ahead.
Yeah. So Chungji mentioned light frontalicity, which is really very convenient because it really is the physics of conservation of the angular momentum. And particularly, you use light cone gauge in gauge theories, and then you avoid the ghosts and so on. So it has many advantages to use light front helicities, and that's actually underlies most of the theorems and so on that people talk about when they talk about spin sum rules. It's really in the context of light frontalicity. So I'm glad that Chung mentioned that there's really a distinction. And also I'm glad that the brilliant talk by Philip. I just wanted to say that I agree with this last comment about the vacuum, that in gravity it's one thing. However, in ordinary flat space, if you look at QCD and you start thinking about all the vacuum problems that people talk about in instant form, the question is, what physics really remains in the front form, because the vacuum graphs really are not there in the flat space. So maybe Philip would like to say more about that, because that's really a profound point for physics, that the light front really gives you another way to understand what people often describe to vacuum graphs in lattice gauge theory and instant form, for example. So maybe we could have more comment on that.
Philip, you have a comment?
I don't think I have anything to add beyond what I just said. As far as I'm concerned, the vacuum graph issue is only an issue for gravity. And when you write down the Dyson-Wick expansion, the Wick expansion, you divide out by the vacuum-to-vacuum persistence graph, and you don't need to calculate it. So those things should never be considered in the first place. There is one place, though, where these tadpole graphs do play a role beyond gravity, and that is in spontaneous breakdown. Namely, you can have a scalar field go into the vacuum carrying zero form momentum. It can go into the tadpole. And I think if you go all the way back to the work of Ben Lee in about 1972 or so, you sum the infinite set of vacuum bubbles, and they take you into a new vacuum. They force you out of the vacuum in which the expectation value of scalar field phi is zero into a vacuum in which its expectation value is non-zero. So certainly the tadpole graphs are important if you were to start in the wrong vacuum, namely the free vacuum, the one in which you think the expectation value of phi is zero, and you wanted to discover, is it the true vacuum? And the answer is, you have to sum an infinite number of bubbles, because if you sum a finite number, you can't change the Hilbert space. That's just perturbation theory. If you want to get a new Hilbert space, namely a different vacuum where expectation value of phi is non-zero, you have to sum an infinite set of graphs. And those graphs cannot be ignored. So the tadpole graph, and remember, these are all graphs where zero momentum is coming in at the cross, and therefore the only momentum that contributes in the loop is the one with p minus equals zero. Now, Stanley is absolutely correct that if you don't have that situation, if you have non-zero momentum, then everything is fine. Then you don't have to worry about zero modes at all. And the light front is a very convenient way to do things. But if you are explicitly concerned about spontaneous symmetry breaking, and that doesn't mean showing that you have a broken vacuum, but showing that the unbroken vacuum is not stable, then you have to include all the tadpole graphs.
Yes.
Thank you.
Well, I'll just add that the Higgs theory in the front form is exactly what you say. You really have to do spontaneous symmetry breaking to recover the usual Higgs theory. The thing that keeps bothering me is whether QCD itself ever has this type of issue. The Higgs theory is very special.
Well, I could give a whole lecture on why QCD doesn't have a Higgs phase, and it's all related to anomalous dimensions, but that's a whole different topic. I believe that the only way to ever do the Higgs mechanism is you have to do it dynamically by having expectation value of psi bar psi be non-zero, and if you introduce a minus mu squared phi squared into the Lagrangian, I think that has nothing to do with the real world. But that's a whole different topic which we couldn't cover in the time we have now.
That really falls into the...
We'll talk more about that sometime, Peter.
Yeah, hopefully. We will have John Collins speaking about zero mode issues, and I think they will come up also in talks concerning GPDs and other issues. So this is not a subject that will be overlooked in future seminars, I think. And because of time constraints at this point, we have to end the discussion. But thank you very much, Philip, for your talk. And in 2 weeks, we will have another topic, mesons and other things, beta-salpeter amplitudes and form factors by Peter Maris. Thank you for everybody for coming to the seminar, and see you in 2 weeks. Thank you. Bye.
Goodbye.
Goodbye. Thank you.